Filippo, and his interesting fact is he's probably the only person in the world to have done this. He had an article that was at the top of the Rust Reddit thread and the top of the Golang one. It was the same article at the same time.
Very fancy.
All right. Hello, everyone. Okay, so those here in the audience that had the misfortune of working with Seago before know that it's a way to call code written in other languages, like C, from your code that is written in Go. More in general, we call those kind of things foreign function interfaces, because they allow you to interface with code written in foreign languages, foreign code. Seago is made of a lot of parts. There's a code generation tool that generates all the boilerplate to connect the two sides of the functions. There's the internals of the FFI that allow you to actually invoke the pointers, set up the stack, manage threads and such, which are in the compiler. And then there's, which are there to make the C code happy when it's executing. Then there's safety features, which are meant instead to make the Go code less unhappy about what you're doing to its poor memory, which include things like making sure you don't pass pointers that the garbage collector will then move, and similar rules. And finally, there's some utility libraries and some types that help you develop code for Seago. But I'm not here to talk about Seago. I'm here to tell you how to build your own FFI. Now, why you would want to do this, it's not in scope. There are a number of bad reasons, and I suppose good ones. But today we're going to talk about how you would do that and what we can learn by doing that, of course. So, FFI is made of a few core pieces. You need, fundamentally, a way to put the code together, to make the code sit next to each other in a package, and then to end up in the same binary so that it can be executed. Then you need some way to jump from your foreign code, from your Go code, into your foreign code. You need some way to tell the Go code what function you want to call from outside Go world. And finally, you need a way for those two functions to share arguments, share return values, and share memory. They need to agree on where they will find each of those and how they will treat them. Make sense? And of course, you're going to need a piece of foreign code. Now, what is everyone's favorite non-Go language? Shout it out.
Rust.
More. Haskell, Python, C#, all wrong. It's Rust. Good. Now that you know why I'm really here, let me present you with this piece of organic, grass-fed, standard library-free Rust code. It performs a task for which you need the utmost safety and performance. It multiplies numbers by 2. And it compiles into a nice little static library. Now, we'll try to make use of this important function from our Go code without touching Seago. As we said, the first thing we need is a way to compile this foreign code together with the Go code. And sadly, there is no go build -- include this Rust library flag, so we'll have to make do with something lower level. Thankfully, go build is nothing else than a wrapper for smaller tools. And if you run go build -x when you're building a binary, it will actually tell you all the different things it's calling while it does that. And you'll see that first there's compile, and then there's a link, and finally takes the output and puts it in your folder as the binary. for those like me that didn't have the occasion to study how compilers work, the idea is that the compiler takes some code, like Go, and the Go compiler, common compile, takes code in groups of packages, and compiles it into object files. Object files are a collection of symbols and the code that represents them. Symbols are things like your function name. A function name is a symbol along with the code that executes that function. And these object files, .o files, are collected together in .a files, which are very little more than a list of files. In this case, object files. And finally, there's a linker. The linker instead is tasked with making the final binary and making it by putting together all these object files inside these archive files. The Go compiler has its own linker. It's called command link. And it's what we usually refer to when you hear the expression internal linking. Who heard of internal or external linking here? Good. I was worried there would be more hands up because this should really be a detail that is hidden from you. But there were things like DNS reasons for why you would end up having to know about this. So the internal linker is a linker, indeed something that can build a binary from a set of object files that is implemented entirely in Go. It's originally from the Plan 9 linker. And it's why cross-compilation in Go is so wonderful. The linker is a Go program that can make an output for each of the supported platforms, and it doesn't care where it's running, because it's just a Go program that in turn you can cross-compile. So when you want to cross-compile something in Go, you just tell the linker, you know what, I don't want a binary for my Mac on AMD64. I actually want a binary that will run on my Raspberry Pi on Linux with ARM. And it will just do that. This, of course, is incredibly useful. But making a linker is a big task, and supporting all kinds of different, they're called relocations, the ways things are connected together between object files, is overkill. So instead, when you need to link something that is not just Go code, which is not made by command compile, so might contain all sorts of weird stuff, instead what command link does is that it invokes a linker from your system. That linker will have implemented everything, or will be able to access dynamic libraries. Now, the problem with this is that usually that linker has a specific target, so it can't cross-compile. And this is why we can't cross-compile CGO easily. But one thing that we can do with external linking is just pass it another flag and tell it, hey, by the way, could you also include this static library I have sitting over here when you're linking? And we're done. That's it for compiling code together. But that only works if we control the linking step. What if we want instead to distribute a package that you can import and not have to write weird makefiles to link it into a binary? Well, then we look at what GoBuild does to build packages. And looking at that, we see a familiar compile step that makes a .a and nothing else. That's what it does. It will make the .a and it will save it into that. So it will do the compile step and then save it into that GoPath PKG folder that you might have noticed and wonder what it was. There is where all the .a files, which are pre-compiled packages, live for the next time you need to link them into a binary. This is the concept of incremental builds. So something we could do is go mess with that .a file, try to push things inside that archive. So what handles .a files? The R tool. There's a reason this rhymes with tar, and it's that tar pretty much obsoleted R in day-to-day use. R is still used, I believe, for Debian packages and putting together object files into libraries, and that's it. It's a very simple format that, of course, has 1,000 different variations because it's a Unix tool. The original variation has a maximum file length of file name length of 15 bytes, which doesn't. There are extensions, but the Go archive tool, which is common pack, uses the original R-style Unix. As a lot of things in Go if you start to dive into the internals. So, okay, we know how to manipulate these archive files. We know that these .a files is where the code for a package lives. Can we just take our Rust archive, extract it, get all the object files out, and then pack it back into the .a file of the Go package? So we take our libmultiplication.a, which is the Rust static library, extract it, same option as tar, and then we put it back into the .a file in GoPath PKG. Turns out that this very nearly works. Works for some subset of linkers and platforms. But sadly, what breaks the others is that now you have objects inside your .a that have no business being there. They were just there because the Rust compiler generated them for reasons. And tools maybe try to link to libc, which we don't know, we don't want to have anything to do with because we're compiling Go. So instead, what we can do is learn how the linker works and use it to generate a reusable .o file. Instead of extracting the archive, we run LD, the linker, the platform linker, and we make it generate a single .o file that is generated by starting a tree from the function we care about, multiply2, because that's what we hope to invoke eventually. And all the things multiply2 calls and needs are put into that .o object, and nothing else. Because we used the --gc section, garbage collect sections option. We take that .o and we use common pack to put it into our Go package in gopath/package. And that's it. So what we did is we compiled some foreign code and we found a way to put that foreign code into a package together with the Go code. They don't talk to each other yet, but they're sitting next to each other, so the linker will find them both. How we did it is by using the linker and common pack. So far, so good? OK. So now that we put the code together, we kind of need to now do the jump, somehow call the function from Go that we just put there. They're not going to do anything by sitting next to each other. So to do that, we're going to need to learn a bit of GoAssembly language. Who here ever did GoAssembly? More than I thought. How it works might be familiar also to who's have developed C or C++, because you need to somehow, the compiler and the assembler run in parallel. And you need to somehow tell the compiler that this function totally exists, it will exist eventually, and it takes these parameters and it returns these values. Otherwise, how would you know the types? How would you know the function exists? So how you do it is by putting a header, just like a C header, in the Go file, which is a function without the body, without the implementation. And then you go into your .s file, which is your assembly file, and you define a function in assembly. That same function with the same name. Govet will also be helpful and check that you didn't make mistakes between the definition and the actual code. Now that we can do that, we can try different ways of calling our multiply2 function. The first thing that might come to mind is, I know, I'll write a header for the multiply2 function. That doesn't work. And a number of other things I tried that didn't work, and for 5 days I kind of abandoned the project. But then I was diving into the Seago for other reasons, and I realized that Seago does this, right? And Seago is only a code generator. It generates some code that makes the jump. So if Seago can generate it, we can probably copy-paste it. So if we look in the Seago source, we find where, for example, it writes how to reach malloc, a C function. And there is one specifically interesting stanza there. Seago import static. That's the key. That's what tells the compiler, yes, I'm invoking this function. You have no idea what it is. There is no definition. It's not in the assembly files, but eventually it will exist. Just trust me. And we do that, and once we have that, plus some cleverness that I don't want to go over to take a pointer of that function instead of just the name, we can go into our assembly and simply take the pointer, put it into a register, and jump there. This, of course, crashes, but it does reach the Rust code. So we did the jump. What we did is that we got the linker to put the pointer to our Rust function in a Go variable, so that we can then jump using assembly into it. It won't do anything useful, but first we put the code together. Then we made a variable that points to our code in the foreign language. So far, so good? OK. Final step. We need them to agree. We need them to behave the same way. We need them to do arguments and return values and calling conventions the same way. But what's this thing? What's a calling convention? That's what keeps the entire linking ecosystem together. Because as I said, symbols are just code. There's only a convention that says how this function call each other, and when they call each other, what do they expect from the caller? Where is my stack? Where are my arguments, and where do I put the return values once I calculated them? And there is a very standard one, which is a very common one, which is the C calling convention. That's what CGO targets. That's also what Rust exposes when you ask it to expose something fixed. And then there's the Go calling convention. It's completely different. And sadly, very undocumented. So what we will do first is try to dive into the Go calling convention. Then we will quickly see how the C calling convention differs. And since all the documentation we have is the Go doc of the assembler and one specific slide from an IBM talk a few years ago, we're going to use something else. So what we're going to use here is a debugger. We're going to take the debugger and stop the program at the right point when it's about to make a function call and stare at what it's doing to learn what we are supposed to do. Because that never broke. Good. So the first thing we need is a guinea pig. We're going to take a function that takes a number, returns a number, which happens to be a slower implementation of multiply too. But we'll take it, compile it with Go, and disassemble it. Our argument is that string of 5s. So the first thing we look for is that string of 5s. And we find that being loaded and copied directly into the stack. So what we learn is that arguments are passed by passing them to the stack. The stack, very briefly, I can't really explain the little time we have, but it's where memory it's one of the two ways programs usually store memory, and it has a fixed structure where you keep adding things and the others keeps going down. So it adds the argument to the stack and then executes a call instruction. The call instruction is a native instruction that jumps into the function and pushes to the stack where it came from, so that it can then go back when the function completed its execution. Makes sense. Then the first thing that our callee, the callee is the function that is being called, does is a preamble to check that it has enough stack. We can skip that. And then it manages the stack pointer. Now, this will get completely unfollowable without a diagram. So here is a diagram where you have the stack of the caller on this side and the stack of the callee on the other side. As you can see, they overlap because the arguments and the return values are used both by the caller and the callee. And you can see that the stack grows down every time you add something. So Well, the first thing it does is that it moves the stack pointer, the things that says where is the bottom of the stack, to the bottom of all the local variables it will use. So Go doesn't actually use push instructions. It just moves the thing all the way down immediately and then stores things where it knows to store things. Next, we save the frame pointer. The frame pointer is a way to be very fast at unrolling stacks. So your program crashed, or you want to know the performance of your program, and you want to know what it's doing right now. You look at the stack, and you take this register. It always points to the frame pointer. And there you find the previous value of that register, which points to the caller frame pointer. And you keep going up. And what that allows you to do is find the return value, which is sitting just on top of the frame pointer. And each return value tells you a function in the call stack. So this is for fast debugging and profiling. Interestingly, I don't think the Go runtime uses this much, but it's in there so that the Go executable are compatible with tools like perf, for example, just out of the box. So we push that, and then we see that the function loads an argument. And we learn that, indeed, arguments are at the bottom of the caller stack. Then it does the computation, and it returns the value. And it returns it by writing it just above the argument. So this is what we learned of the Go calling convention. The Go calling convention, it's entirely stack-based. The arguments are on the stack, the return values are on the stack, there are frame pointers on the stack, there are return values. So this is enough to try to make something that uses it. We also need to understand what we have on the other side, the C calling convention. The C calling convention is pretty different. It still uses call instructions and frame pointers, but it doesn't pass arguments on the stack, it passes them on as registers. And the return values as well are in a register, single register, not on the stack. The problem Go would have with this is that a lot of Go types are wider than a single register, and you can return an entire wide type. Or even you can return multiple values. So you would have to, Go would have to secretly make a structure and then pass the pointer back, and that would get more complex. Finally, the stack has to be aligned at the 16 bytes modulo. That's what tripped me up at the beginning, and why using jump was working, but call wasn't before we studied the calling convention. So this is what Rust uses. We know what Go uses. We should be ready to write a bit of assembly that will act as a trampoline. It will load things from the Go stack according to the Go calling convention, and it will execute the Rust function that we learned how to link to and that we put in the same binary using the C calling convention. It also aligns the stack and cleans up when it's done and take the return value and put it where it's expected to be. This, by the way, is exactly what CGO does. If you go look in the source for ASMC Go call, you find a function that does a lot more fancy things, but at the end of the day, it does this. So to recap, we had our main package that is using our hybrid library. It calls a function from the package, multiplication.multiply by 2. And the function is in the package is implemented by this trampoline in Go assembly. It takes the argument and passes it onto the Rust function. And finally, the Rust implementation is like this. It exposes the C ABI and does the multiplication. With all those pieces, we can run cargo to compile Rust. We can use the linker to then boil it down to a single object file. We can use the Go tooling to make a .a that comprehends both the Go assembly, the Go code, and our object file in Rust. We install it in PKG. We run Go build without any flags, without any requirement, as if we were using a normal library. And we get a binary that can multiply 2 by 2. Success! This was 3 months of my life. Good. But there is one thing that we didn't really take good care of. Go is different fundamentally from C in how it handles stacks. C has one stack. You can make other threads if you want more stacks, but that's the stack. It's big, and it can grow, and if you run out of stack, you have a serious problem, so you should probably just crash. Goroutines don't. Goroutines, you can have thousands and thousands in the same execution, and if all of them had enough space to never run out, you wouldn't have even enough virtual space. So instead, what the Go compiler does is that it prepends each function with a small preamble, we saw it briefly before, that checks that there is enough stack space. If not, it stops, makes a new bigger stack, allocates it, copies the entire existing stack to the new one, which is usually double-sized, and then resumes execution. It can do this because the garbage collector has all the metadata about where all the pointers are. Now, we really don't want to teach Rust how to expand the Go stacks. I couldn't bring myself. So instead, what I did is say this trampoline function, it needs a lot of stack. It needs like 2 kilobytes of stack just to multiply two numbers. And then I cheated by rolling back the stack pointer. If you remember, the stack pointer always stays at the bottom of the stack. So what I did is subtract and roll it all the way back up so that this space, I'm sure it's there, and now I can call the Rust function and it will use this, hopefully not use too much. Two things I don't know. What happens if it uses more? And what happens if a debugger tries to figure out who owns that memory? So of course, don't actually use this in production. I'm begging here. This was a learning exercise. Do not go home or go to your workplace and say, no, this needs to go fast. We're going to use Rust Go. OK. So what we did is we made a trampoline that jumps from the Go calling convention to the C one. That was the last step. We now have a bare bones, hackish, but functional FFI that we built ourselves, and it has no CGO. We did use something named CGO, but it just happens to be named like that because it has no actual CGO tool involvement. And we did it by terrible assembly. Final thing that I promised, a bonus. How do you distribute this .a? There's a specific feature. It's called binary-only packages. They allow you to annotate source to say, yes, this is totally the source, but you shouldn't try to compile it. You will find a .a in the PKG folder. Use that. Which is great because the Go compiler would try to recompile the thing if it didn't match up. So we can just make a zip file with the source and the .a's for as many platforms as we can compile it for. And when you unzip it in your Go path, you'll have your thing that you can import normally without even knowing what horrible things we're doing and just carry on with your Go development. Because that annotation says, just look at the .a, which includes all you need to know. So thank you. There is a blog post that goes through all the pain and mistakes I made in the process of figuring this out. It's much longer, but it has more details and reasons things work on OS X and not on Linux. And it finally has a real-world example that uses a Rust cryptographic library to actually outperform a Go cryptographic library. But again, don't use this. Thank you.
That was awesome. Thank you, Filippo.